Buckle up, because we're about to take a wild ride around Neptune, a journey that'll make you question everything you thought you knew about moons. Picture this, a tiny world, hurtling through space in the opposite direction to almost everything else, a cosmic rebel with a surface that looks like a cantaloupe went through a blender. This isn't just any moon. It's Triton, Neptune's enigmatic sidekick, and it's got a story to tell that's out of this world. Stick around, because we're about to uncover the secrets of this retrograde wonder, a captured wanderer from the distant Kuiper Belt, and trust me, you won't want to miss a single second of this. The enigmatic Neptune. Neptune's largest moon, Triton, is a captivating celestial body that orbits its planet in a peculiar manner. Unlike most moons in our solar system, Triton has a retrograde orbit, meaning it revolves around Neptune in the opposite direction to the planet's rotation. This backward motion is a strong indicator that Triton did not form an orbit around Neptune, but was instead captured by the planet's gravity. The moon's unusual trajectory suggests a violent past, likely involving a close encounter with Neptune that slowed Triton down enough for the planet's gravity to seize it. This capture event is thought to have occurred relatively recently, on a geological timescale, and would have caused significant tidal heating and geological activity on Triton. Triton's surface is a mesmerizing landscape, often likened to a cantaloupe due to its distinctive, pockmarked appearance. This terrain is characterized by a complex network of ridges and valleys, giving the moon a wrinkled, almost organic look. The cantaloupe terrain is thought to be the result of extensive tectonic activity, driven by the same tidal forces that likely caused Triton's retrograde orbit. These forces would have stretched and compressed the moon's interior, leading to the formation of the unique surface features we observe today. The moon's icy composition, primarily consisting of nitrogen, water ice, and frozen carbon dioxide, adds to its enigmatic allure. The hypothesis that Triton is a captured Kuiper Belt object is supported by several lines of evidence. The Kuiper Belt is a region of the solar system beyond Neptune's orbit, populated by small, icy bodies. Triton's composition, orbit, and geological activity all align with what we would expect from a captured Kuiper Belt object. Furthermore, Triton's density is lower than that of Neptune's other moons, suggesting it formed in the cold, outer reaches of the solar system, where icy bodies are more common. The moon's retrograde orbit is another clue, as it is uncommon for moons to form in such a manner around their parent planets. Triton's captured origin and retrograde orbit have significant implications for our understanding of the solar system's formation and evolution. The capture of a large moon like Triton by a planet's gravity is a rare and dramatic event, providing insights into the dynamic processes that shaped our solar system. Moreover, Triton's unique characteristics make it a valuable subject for studying the composition and behavior of Kuiper Belt objects. By examining Triton, scientists can gain a better understanding of the icy bodies that populate the outer solar system and the role they played in the solar system's history. The moon's cantaloupe terrain and active geology also offer a window into the processes that shape icy worlds, both within and beyond our solar system. A glimpse into the outer solar system. Triton, Neptune's largest moon, is a captivating enigma nestled in the outer solar system. Unlike most moons, Triton orbits Neptune in a retrograde direction, meaning it moves opposite to the planet's rotation. This peculiar motion suggests that Triton didn't form in place, but was instead captured by Neptune's gravity. The moon's retrograde orbit is a strong indicator of its exotic origins, likely hailing from the Kuiper Belt, a vast region of icy bodies beyond Neptune's orbit. The capture of Triton by Neptune's gravity is thought to have been a chaotic event, potentially disrupting the moon's original composition and structure. One of Triton's most striking features is its cantaloupe-like terrain, a surface covered in irregularly shaped ridges and depressions that resemble the skin of a cantaloupe melon. This unique landscape is thought to be the result of extensive resurfacing events, possibly driven by internal geological activity. The cantaloupe terrain is primarily found in Triton's western hemisphere and is interspersed with smooth plains and icy volcanoes. The moon's surface is predominantly composed of nitrogen, water ice, and frozen carbon dioxide, contributing to its reflective, icy appearance. The interplay of these materials and geological processes has sculpted Triton into a moon that is both visually striking and scientifically intriguing. Triton's captured origins and retrograde orbit have significant implications for our understanding of the outer solar system. The Moon's composition and geological activity provide valuable insights into the conditions and processes that shaped the Kuiper Belt objects from which it likely originated. Studying Triton's surface features and internal dynamics offers a window into the early solar system, revealing how gravitational interactions and capture events can influence the evolution of planetary systems. Moreover, Triton's unique characteristics make it a prime target for future exploration, as it holds clues about the formation and migration of icy bodies in the outer solar system. By unraveling the mysteries of Triton, scientists can deepen their understanding of the broader processes that have shaped our cosmic neighborhood. The discovery of Triton. Triton, Neptune's largest moon, is a celestial body that has long captivated astronomers due to its unique characteristics. Among these, its retrograde orbit stands out. Unlike most of Neptune's moons, which orbit in the same direction as the planet's rotation, Triton moves in the opposite direction. This backward, or retrograde, motion is a strong indicator that Triton did not form an orbit around Neptune, but was instead captured by the planet's gravity. Such captures are not uncommon in our solar system, and they often result from the gravitational interactions between a planet and a passing object, like a comet or, in Triton's case, a Kuiper Belt object. The surface of Triton is a fascinating tapestry of geological features, with the cantaloupe terrain being one of the most distinctive. This terrain is characterized by a series of irregular, cantaloupe-like ridges and depressions that cover a significant portion of the Moon's surface. These features are thought to be the result of icy volcanism, where nitrogen and other volatile substances erupt from beneath the surface, shaping the landscape in a manner reminiscent of the texture of a cantaloupe. The cantaloupe terrain is not uniform, with some areas appearing smoother and others more rugged, hinting at a complex geological history. Triton's captured origin is further supported by its composition and density. The Moon is composed primarily of ice, with a rocky core, and has a density similar to that of other Kuiper Belt objects. This composition suggests that Triton formed in the distant reaches of the solar system, far from Neptune, before being drawn in by the planet's gravity. The capture process would have been a violent one, with Triton's original orbit being circularized and its rotation synchronized with its orbit around Neptune. This violent past is evident in the Moon's geology, with features such as faults and fractures crisscrossing its surface. The retrograde orbit of Triton also has implications for its long-term stability. Over time, tidal forces between Neptune and Triton are causing the Moon to slowly spiral inward, eventually leading to its destruction or transformation. This process is a slow one, taking billions of years, but it is a reminder of the dynamic and ever-changing nature of our solar system. Despite this, Triton remains a fascinating world, with its unique characteristics offering valuable insights into the processes that shape our solar system. An unusual orbit. Triton, Neptune's largest moon, is a captivating celestial body that defies conventional lunar norms. Its most striking feature is its retrograde orbit, a peculiar characteristic that sets it apart from the majority of moons in our solar system. Unlike most natural satellites, which orbit their planets in the same direction as their host's rotation, Triton orbits Neptune in the opposite direction. This backward, or retrograde, motion suggests a violent past, hinting that Triton may have been captured by Neptune's gravity rather than forming in place. The Moon's inclined orbit, tilted about 23 degrees relative to Neptune's equator, further supports this theory. Such an orbit is a strong indicator of an external origin, likely from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. Triton's surface is a mesmerizing tapestry of icy plains and rugged terrain, often likened to the skin of a cantaloupe. This cantaloupe terrain is a result of extensive resurfacing by icy volcanism and tectonic activity. The Moon's surface is relatively young, with few impact craters, indicating that geological processes have been at work relatively recently. The icy plains are interspersed with ridges and valleys, creating a complex and varied landscape. These features are thought to be the result of cryovolcanic eruptions, where water, ammonia, and methane have been spewed onto the surface, freezing and reshaping the terrain. The cantaloupe terrain is particularly striking, with its irregular, polygonal patterns that resemble the skin of the fruit. The combination of Triton's retrograde orbit and its geologically active surface paints a picture of a moon with a tumultuous history. Its captured origin from the Kuiper Belt is further supported by its composition, which is similar to that of other Kuiper Belt objects. Triton is primarily composed of ice, with a rocky core, and its surface is rich in nitrogen, methane, and carbon monoxide ices. These compositional similarities to Kuiper Belt objects provide strong evidence that Triton was once an independent body in the outer solar system before being captured by Neptune's gravity. The capture event itself would have been a violent one, likely causing significant tidal heating and geological activity, which could explain Triton's active past and present. Retrograde motion, a cosmic anomaly. In the vast expanse of our solar system, Neptune's largest moon, Triton, stands out as a peculiar celestial body. Its most striking feature is its retrograde orbit, a cosmic anomaly where it revolves around Neptune in the opposite direction to the planet's rotation. This backward motion is a strong indicator that Triton did not form an orbit around Neptune, but was instead captured by the planet's gravity. Such captures are rare and typically occur when an object, like a moon or a comet, wanders too close to a planet and is ensnared by its gravitational pull. Triton's retrograde orbit is a vivid reminder of the dynamic and often chaotic nature of our solar system's formation. Triton's surface is equally as intriguing as its orbit. It is characterized by a unique terrain known as cantaloupe terrain, named for its resemblance to the skin of a cantaloupe melon. This landscape is composed of a series of intersecting ridges and valleys, creating a hummocky appearance. The cantaloupe terrain is thought to be the result of extensive resurfacing events, possibly driven by internal heat and geological activity. These processes might have been triggered by tidal forces exerted by Neptune, which could have caused Triton's interior to heat up and become geologically active. The moon's surface also features active geysers that spew nitrogen gas and dust, adding to its enigmatic nature. The hypothesis that Triton is a captured Kuiper Belt object is supported by several lines of evidence. The Kuiper Belt is a region of the solar system beyond Neptune's orbit, populated with small, icy bodies. Triton's composition, which includes a significant amount of ice and rock, is consistent with that of Kuiper Belt objects. Additionally, its retrograde orbit and inclined orbit, relative to Neptune's equator, are characteristic of captured bodies. The capture of Triton by Neptune would have been a complex process, likely involving a close encounter followed by a gradual stabilization of the moon's orbit. This capture scenario provides valuable insights into the dynamical evolution of the outer solar system and the processes that shape the orbits of celestial bodies. Triton's captured nature. Triton, Neptune's largest moon, is a captivating celestial body that orbits its planet in a peculiar manner. Unlike most moons in our solar system, Triton moves in a retrograde orbit, meaning it travels in the opposite direction to Neptune's rotation. This backward motion is a strong indicator that Triton did not form an orbit around Neptune, but was instead captured by the planet's gravity at some point in the past. The moon's unique orbit is highly inclined and elliptical, further supporting the theory of its captured nature. This unusual trajectory suggests a violent history, likely involving a close encounter with Neptune that slowed Triton down enough for the planet's gravity to seize control. The surface of Triton is a mesmerizing landscape, often likened to a cantaloupe due to its distinctive, pockmarked terrain. This unusual appearance is the result of extensive geological activity, including cryovolcanism, where icy materials erupt onto the surface instead of molten rock. The moon's surface is also marked by vast, smooth plains, intricate ridges, and valleys, all of which hint at a complex and dynamic history. The cantaloupe terrain itself is thought to be caused by the upwelling of nitrogen and other ices from beneath the surface, creating a pattern reminiscent of a cantaloupe skin. These features provide valuable clues about Triton's internal processes and its evolution over time. Triton's captured nature and retrograde orbit offer compelling evidence of its origins as a Kuiper Belt object. The Kuiper Belt is a vast region of icy bodies beyond Neptune's orbit, and many of these objects share similar compositions and characteristics with Triton. The Moon's high density and rocky core are consistent with the properties of Kuiper Belt objects, further supporting the idea that Triton was once a part of this distant population. Its capture by Neptune would have been a dramatic event, potentially involving a close gravitational interaction that altered Triton's trajectory and brought it into orbit around the planet. This capture scenario is not unique to Triton. Other retrograde moons in our solar system, such as Saturn's Phoebe, also exhibit similar characteristics and are believed to have been captured from the outer solar system. The mystery of its origin. Triton, Neptune's largest moon, is a celestial body shrouded in enigmas, none more intriguing than its retrograde orbit. Unlike the majority of moons in our solar system, which orbit their planets in the same direction as their parents' rotation, Triton circles Neptune in the opposite direction. This backward, or retrograde, motion is a strong indicator that Triton did not form an orbit around Neptune, but was instead captured by the planet's gravity. The Moon's inclined orbit, which is highly tilted relative to Neptune's equator, further supports this capture hypothesis. Such orbital characteristics are typical of objects that have been gravitationally snared from elsewhere, rather than those that have coalesced in situ. The surface of Triton is a stark and captivating landscape, dominated by what scientists have dubbed the cantaloupe terrain. This unusual geological feature is a vast, undulating region covered in irregular, cantaloupe-like bumps and depressions. These formations are believed to be the result of icy volcanic activity, or cryovolcanism, where mixtures of nitrogen, methane, and water ice have erupted from Triton's interior and reshaped its surface. The cantaloupe terrain is a testament to Triton's dynamic geological history, hinting at a complex internal structure and ongoing processes that continue to mold the Moon's appearance. Triton's captured origin is further hinted at by its composition and density. The Moon's density is slightly higher than that of Neptune's other moons, suggesting a different origin story. Its surface is rich in nitrogen, carbon monoxide, and methane ices, which are also found in the Kuiper Belt, a region of the solar system beyond Neptune's orbit populated by small, icy bodies. This chemical kinship with Kuiper Belt objects, KBOs, strengthens the argument that Triton was once a part of this distant realm before being captured by Neptune's gravity. The Moon's size and composition are also consistent with those of the larger KBOs, adding another piece to the puzzle of Triton's mysterious past. The capture of Triton by Neptune would have been a violent and chaotic event. As Triton ventured too close to Neptune, the planet's gravitational pull would have exerted a tremendous force on the Moon, potentially stripping away its outer layers and heating its interior. This catastrophic encounter could explain Triton's current orbital characteristics and the extensive resurfacing of its cantaloupe terrain. The energy dissipated during the capture event might have also driven the differentiation of Triton's interior, leading to the separation of its rocky core from its icy mantle. This process would have set the stage for the subsequent geological activity that has sculpted Triton's surface over time. A frozen world. Triton, Neptune's largest moon, is a captivating celestial body that orbits its planet in a peculiar manner. Unlike most moons in our solar system, Triton moves in a retrograde orbit, meaning it travels in the opposite direction to Neptune's rotation. This backward motion is a strong indicator that Triton did not form an orbit around Neptune, but was instead captured by the planet's gravity. The Moon's unusual orbit is not circular but highly elliptical, further supporting the theory of its captured origin. Scientists believe Triton was once a solitary object in the Kuiper Belt, a region of icy bodies beyond Neptune, before being drawn into Neptune's gravitational pull. The surface of Triton is a mesmerizing landscape, often likened to a cantaloupe due to its distinctive terrain. This terrain is characterized by a complex network of ridges and valleys that crisscross the Moon's surface, creating a pattern reminiscent of a cantaloupe's skin. The ridges, which can reach heights of up to 10 meters, are thought to be the result of icy volcanic activity, a process known as cryovolcanism. These eruptions spew a mix of nitrogen, methane, and water ice, shaping the Moon's surface over time. The valleys, on the other hand, are likely formed by the sublimation of nitrogen ice, where the ice transitions directly from solid to gas, leaving behind depressions. Triton's frozen world is a testament to its frigid environment. The moon's surface temperature hovers around -235 degrees Celsius, making it one of the coldest objects in the solar system. This extreme cold is responsible for the vast polar caps of nitrogen ice that cover Triton's surface. These caps are not static but undergo seasonal changes, growing and shrinking in response to the moon's eccentric orbit. The polar caps are also home to geysers that erupt from beneath the surface, spewing nitrogen gas and dark particles into the thin atmosphere. These geysers are another example of Triton's active cryovolcanism, which continues to shape and reshape its frozen landscape. The combination of Triton's retrograde orbit, cantaloupe terrain, and frozen world paints a picture of a moon with a complex and dynamic history. Its captured origin from the Kuiper Belt, coupled with its active geological processes, makes Triton a fascinating subject of study for scientists. The moon's unique characteristics provide valuable insights into the formation and evolution of our solar system. As we continue to explore and understand Triton, we gain a deeper appreciation for the diverse and wondrous objects that populate our cosmic neighborhood. Cryovolcanism, ice fountains of Triton. Triton, Neptune's largest moon, is a captivating celestial body that defies conventional lunar norms. Unlike most moons in our solar system, Triton orbits Neptune in a retrograde direction, meaning it moves in the opposite direction to its planet's rotation. This peculiar behavior strongly suggests that Triton did not form an orbit around Neptune, but was instead captured by the planet's gravity. The leading theory proposes that Triton originated in the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. This captured origin explains Triton's unique characteristics, including its retrograde orbit and its composition, which is rich in nitrogen, methane, and water ice. One of Triton's most striking features is its cantaloupe terrain, a bizarre landscape that resembles the skin of a cantaloupe melon. This terrain is characterized by a series of irregular, crater-like depressions that are interconnected by ridges and troughs. Scientists believe that this unique topography was formed by a process called diapirism, where less dense material rises through a denser layer, creating a distinctive pattern. The cantaloupe terrain is a testament to Triton's dynamic geological history, which includes extensive resurfacing events that have erased many of the moon's older impact craters. Triton's geological activity is not limited to its cantaloupe terrain. The moon is also home to active cryovolcanism, a process where volatile compounds such as nitrogen and methane are ejected from the interior onto the surface. These icy eruptions create spectacular plumes that can reach heights of up to 8 kilometers. The most famous of these plumes was observed by the Voyager 2 spacecraft in 1989, which captured images of dark, geyser-like eruptions spewing material into the thin atmosphere. These eruptions are driven by the heating of Triton's interior, possibly due to tidal forces exerted by Neptune or the decay of radioactive elements. The result is a dynamic and ever-changing surface, marked by a complex interplay of ice, gas, and geological forces. The combination of Triton's retrograde orbit, cantaloupe terrain, and active cryovolcanism makes it one of the most intriguing moons in our solar system. Its captured origin from the Kuiper Belt provides a unique window into the early solar system's dynamics. The moon's geological activity, driven by internal heating and tidal forces, offers insights into the processes that shape icy bodies in the outer solar system. Triton's enigmatic nature continues to captivate scientists and stargazers alike, serving as a reminder of the solar system's vast and varied landscapes. The Great Dark Spot, Triton, Neptune's largest moon, is a captivating celestial body that orbits its planet in a retrograde motion, meaning it moves in the opposite direction to Neptune's rotation. This peculiar behavior strongly suggests that Triton was not born in Neptune's vicinity, but was instead captured by the planet's gravity. The moon's retrograde orbit is a strong indicator of its exotic origins, likely hailing from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. This capture scenario is supported by Triton's inclined orbit and its unusual composition, which differs significantly from Neptune's other moons. The surface of Triton is a mesmerizing landscape, often likened to a cantaloupe due to its distinctive, pitted appearance. These pits, or depressions, are thought to be the result of icy volcanism or subsurface eruptions, which have shaped the moon's terrain over time. The cantaloupe terrain is not uniform. It is interspersed with smooth plains, mounds, and even vast polar caps composed of nitrogen ice. These features paint a picture of a geologically active world, where cryovolcanic processes and seasonal changes continually reshape the surface. The interaction between these geological processes and the moon's retrograde orbit creates a dynamic environment that is unlike any other in our solar system. One of Triton's most intriguing features is the Great Dark Spot, a large, dark region that stands out against the moon's predominantly icy surface. This enigmatic spot is thought to be a vast deposit of dark, organic material, possibly the result of complex chemical reactions driven by the moon's unique environment. The Great Dark Spot's dark hue contrasts sharply with the surrounding icy plains, making it a prominent feature in images captured by spacecraft. Its exact nature and origin remain subjects of scientific debate, with theories ranging from geological activity to the deposition of dark material from external sources. The spot's presence adds another layer of complexity to Triton's already fascinating story, hinting at the moon's rich and varied history. Triton's retrograde orbit and the Great Dark Spot are just two pieces of the puzzle that make this moon so intriguing. The moon's captured origin story, combined with its active geology and unique surface features, offers a wealth of information about the processes that shape our solar system. Studying Triton provides valuable insights into the dynamics of planetary capture, the evolution of icy bodies, and the potential for exotic geology in the outer solar system. As our understanding of Triton continues to grow, so too does our appreciation for the diversity and complexity of the worlds that inhabit our cosmic neighborhood. A thin, wispy atmosphere, Triton, Neptune's largest moon, is a captivating celestial body that orbits its planet in a peculiar retrograde motion. This means it moves in the opposite direction to Neptune's rotation, a behavior that strongly suggests it didn't form in place, but was instead captured by Neptune's gravity. The moon's unusual orbit is just one piece of the puzzle that hints at its violent past, likely originating from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. This captured origin story is supported by Triton's unique characteristics, which set it apart from other moons in the solar system. One of Triton's most striking features is its cantaloupe-like terrain, a bizarre landscape covered in irregular, cantaloupe-like patterns. These patterns are thought to be the result of extensive resurfacing events, possibly driven by cryovolcanic activity, where water, ammonia, and methane erupt onto the surface. The terrain is a mix of smooth plains, mounds, and pits, creating a visually stunning and geologically complex surface. This terrain, combined with its retrograde orbit, paints a picture of a moon that has undergone significant changes since its capture by Neptune. Triton's thin, wispy atmosphere is another intriguing aspect of this mysterious moon. Composed primarily of nitrogen with traces of methane and carbon monoxide, the atmosphere is so thin that it's more accurately described as a surface-bound exosphere. This tenuous atmosphere is subject to dramatic changes, with seasons causing significant variations in surface pressure and temperature. During Neptune's summer, the atmosphere can thicken slightly, while in winter, it may nearly disappear. The atmosphere's composition and behavior provide clues about Triton's internal processes and its interaction with Neptune's magnetosphere. The moon's atmosphere also plays a role in its unique surface features. Nitrogen geysers have been observed erupting from Triton's surface, likely driven by solar heating. These geysers contribute to the moon's thin atmosphere and create dark streaks on the surface, adding to its complex and dynamic landscape. The interaction between Triton's atmosphere, surface, and internal processes makes it a fascinating subject for study, offering insights into the dynamics of icy bodies in the outer solar system. Understanding Triton's atmosphere and surface features can also shed light on the broader processes at play in the Kuiper Belt and other icy regions of the solar system. Nitrogen geysers. Triton, Neptune's largest moon, is a captivating celestial body that orbits its planet in a retrograde motion, meaning it moves in the opposite direction to Neptune's rotation. This peculiar behavior strongly suggests that Triton is not an original satellite of Neptune, but rather a captured object from the distant Kuiper Belt. The Moon's unique orbit is not the only intriguing aspect. Its surface is a patchwork of strange, cantaloupe-like terrain, characterized by irregular, cantaloupe-like ridges and depressions. These features are thought to be the result of extensive geological activity, possibly driven by the internal heat generated by tidal forces exerted by Neptune. The cantaloupe terrain covers a significant portion of Triton's surface, particularly in the Western Hemisphere. It is composed of a series of irregular, intersecting ridges and troughs that resemble the skin of a cantaloupe melon. Scientists believe that these features were formed by a combination of endogenic processes, such as cryovolcanism and diapirism, which are driven by the movement of icy materials beneath the surface. The exact mechanisms behind the formation of this terrain are still not fully understood, but it is clear that Triton has experienced a complex geological history. One of the most striking features of Triton is its active nitrogen geysers, which were first observed by the Voyager 2 spacecraft during its flyby of the Neptune system. These geysers erupt from the surface, spewing nitrogen gas and dark particles into the thin atmosphere. The geysers are thought to be powered by the sublimation of nitrogen ice, which is converted directly from a solid to a gas due to the heat from the sun. This process creates a high-pressure environment beneath the surface, leading to the explosive release of gas and particles. The geysers are not evenly distributed across Triton's surface, but are concentrated in the southern hemisphere, particularly in the region known as the cantaloupe terrain. The presence of nitrogen geysers on Triton provides valuable insights into the Moon's internal structure and composition. The fact that these geysers are active suggests that there is a significant amount of nitrogen ice beneath the surface, which is being continually replenished. This, in turn, implies that Triton has a complex internal structure, with layers of different ices and possibly even a subsurface ocean. The study of these geysers can also shed light on the processes that drive geological activity on icy moons and other small bodies in the outer solar system. By understanding the mechanisms behind these geysers, scientists can gain a better understanding of the conditions that prevail in the distant reaches of our solar system. Triton's tidal interactions. Triton, Neptune's largest moon, is a captivating celestial body that orbits its planet in a retrograde motion. This means it moves in the opposite direction to Neptune's rotation, a behavior that sets it apart from most other moons in our solar system. Such an orbit is a strong indicator that Triton did not form an orbit around Neptune, but was instead captured by the planet's gravity. This capture likely occurred billions of years ago, with Triton originally being a Kuiper Belt object, a remnant from the early solar system. The Moon's retrograde orbit is not just a quirk of its past. It plays a crucial role in the tidal interactions that shape Triton's geology and internal structure. Tidal interactions occur when the gravitational forces between two bodies cause deformation in one or both. In Triton's case, its retrograde orbit around Neptune creates unique tidal forces. These forces generate heat within Triton due to the constant flexing and squeezing of its interior. This process, known as tidal heating, is thought to be responsible for the geological activity observed on Triton's surface. Despite its distance from the Sun, Triton is one of the few moons in the outer solar system that shows signs of recent geological activity, including cryovolcanism and a thin but dynamic atmosphere. One of the most striking features of Triton's surface is its cantaloupe terrain. This unique landscape is characterized by a series of irregular, cantaloupe-like patterns that cover a significant portion of the Moon's surface. The cantaloupe terrain is believed to have formed as a result of the diapiric upwelling of less dense material from Triton's interior. This process is likely driven by the tidal heating caused by Triton's retrograde orbit. The resulting patterns are a testament to the complex interplay between the Moon's internal dynamics and the external tidal forces exerted by Neptune. Triton's retrograde orbit also has implications for its long-term stability. Over time, tidal interactions between Triton and Neptune are causing the Moon's orbit to decay. This means that Triton is gradually moving closer to Neptune. In the distant future, this process could lead to Triton crossing the Roche limit, the point at which tidal forces would tear the moon apart. However, this is a slow process that will take billions of years to occur. For now, Triton remains a fascinating example of the dynamic and complex interactions that can occur between a planet and its moons. The cantaloupe terrain. Triton, Neptune's largest moon, is a captivating celestial body that orbits its planet in a retrograde motion. This means it moves in the opposite direction to Neptune's rotation, a strong indicator that Triton did not form in place, but was instead captured by Neptune's gravity. The moon's unusual orbit suggests a violent past, likely involving a close encounter with Neptune that slowed Triton down enough for the planet's gravity to capture it. This capture event is thought to have been chaotic, potentially tilting Neptune's axis and disrupting other moons in the system. The retrograde orbit is just one piece of the puzzle that paints Triton as a captured Kuiper Belt object, a remnant from the early solar system. One of Triton's most striking features is its unique surface, known as the cantaloupe terrain. This name comes from the moon's wrinkled, bumpy appearance, reminiscent of a cantaloupe melon's skin. The terrain is characterized by irregular, crater-like depressions and ridges that crisscross the surface, creating a complex and intriguing landscape. These features are thought to be the result of icy volcanism, a process where nitrogen and other volatile compounds erupt from beneath the surface, reshaping the moon's geography. The cantaloupe terrain covers a significant portion of Triton, particularly in the Western Hemisphere, and provides clues about the moon's geological history and internal processes. The cantaloupe terrain's origins are deeply tied to Triton's captured nature. As a former Kuiper Belt object, Triton would have been subjected to intense tidal forces during its capture by Neptune. These forces could have heated the moon's interior, leading to the outgassing of volatiles and the formation of the unique surface features seen today. The terrain's complex patterns suggest a history of multiple eruptions and resurfacing events, indicating that Triton has been geologically active, at least in its past. The moon's thin atmosphere, composed mainly of nitrogen, further supports the idea of ongoing or recent geological activity, as this atmosphere is likely replenished by volcanic outgassing. Triton's cantaloupe terrain also offers insights into the moon's composition and structure. The depressions and ridges are thought to be the result of the upwelling of less dense material from beneath the surface, similar to the processes that create volcanic features on Earth. However, on Triton, these materials are likely to be ices rather than molten rock. The terrain's irregular patterns suggest a complex interplay of forces, including the moon's internal heat, the effects of tidal forces from Neptune, and the cycling of volatiles between the surface and the atmosphere. Understanding these processes can provide valuable information about the conditions in the early solar system and the evolution of icy bodies in the Kuiper Belt. A youthful surface. Triton, Neptune's largest moon, is a captivating celestial body that orbits its planet in a peculiar manner. Unlike most moons in our solar system, Triton moves in a retrograde orbit, meaning it travels in the opposite direction to Neptune's rotation. This backward motion suggests that Triton was not born in orbit around Neptune, but was instead captured by the planet's gravity. The moon's unusual trajectory hints at a violent past, possibly involving a close encounter with Neptune that slowed Triton down enough for the planet's gravity to seize it. This capture event likely occurred billions of years ago, reshaping Triton's destiny and leading to its current, youthful appearance. One of the most striking features of Triton is its cantaloupe-like terrain. This distinctive surface is characterized by a complex network of ridges and valleys that resemble the skin of a cantaloupe melon. The terrain is thought to have formed from a combination of geological processes, including cryovolcanism and tectonic activity. Cryovolcanism involves the eruption of icy materials, such as water, ammonia, and methane, which freeze upon reaching the surface. These eruptions can create intricate patterns and shapes, contributing to the moon's unique appearance. Tectonic activity, on the other hand, involves the movement of Triton's icy crust, which can lead to the formation of ridges and faults. The interplay between these processes has resulted in a surface that is both visually stunning and scientifically intriguing. Triton's youthful surface is a testament to its active geological history. Despite its age, the moon's surface appears relatively young, with few impact craters compared to other moons in the solar system. This lack of craters suggests that Triton's surface is continually being resurfaced by geological activity. One possible explanation for this activity is tidal heating, which occurs when Triton's orbit is slightly elliptical, causing it to experience varying gravitational forces from Neptune. These forces generate heat within the moon, driving geological processes that resurface its exterior. Additionally, Triton's retrograde orbit and captured origins imply that it may have originated in the Kuiper Belt, a region of the solar system beyond Neptune's orbit. Kuiper Belt objects are rich in volatile ices, which can contribute to the moon's active geology and youthful appearance. The cantaloupe terrain is not the only unusual feature on Triton's surface. The moon also boasts a variety of other geological wonders, including vast polar ice caps, active geysers, and a thin atmosphere. The polar ice caps are composed primarily of nitrogen ice, which sublimates, turns directly from solid to gas, during the summer, creating a temporary atmosphere. This atmosphere is thin and tenuous, but it plays a crucial role in shaping Triton's surface. Geysers, or cryovolcanic plumes, have been observed erupting from Triton's surface, spewing nitrogen gas and dark particles into the atmosphere. These plumes can reach heights of up to 8 kilometers and are thought to be driven by the sublimation of nitrogen ice beneath the surface. The combination of these features makes Triton a dynamic and fascinating world, offering valuable insights into the processes that shape our solar system. The case of the missing craters. Triton, Neptune's largest moon, is a celestial body shrouded in mysteries. One of its most puzzling features is its retrograde orbit, meaning it moves in the opposite direction to Neptune's rotation. This peculiar motion suggests that Triton didn't form an orbit around Neptune, but was instead captured by the planet's gravity. The leading theory points to Triton's origins in the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. This capture event likely occurred early in the solar system's history, and it's a rare occurrence that provides valuable insights into the dynamic processes that shaped our planetary system. Triton's surface is a tapestry of geological wonders, with one of the most striking features being its cantaloupe terrain. This unique landscape is characterized by a series of irregular, cantaloupe-like bumps and depressions that cover a significant portion of the moon's surface. The origin of this terrain is still debated among scientists, but it's thought to be the result of extensive resurfacing events, possibly driven by internal heating and cryovolcanic activity. The cantaloupe terrain is a testament to Triton's complex geological history and its active past. The case of the missing craters on Triton adds another layer to its enigmatic nature. Unlike many other moons in the solar system, Triton's surface is relatively smooth and lacks a significant number of impact craters. This scarcity of craters suggests that Triton has undergone extensive resurfacing processes that have erased or buried many of the craters that should have accumulated over billions of years. One possible explanation for this is the presence of active geysers and cryovolcanoes that have deposited fresh material onto the surface, effectively repaving it and removing the signs of past impacts. Another factor could be the moon's thin atmosphere, which might play a role in eroding or filling in craters over time. The combination of these processes paints a picture of a moon that is far from geologically dead, but rather one that is still evolving and changing. Triton's unique tidal heating. Triton, Neptune's largest moon, is a captivating celestial body that defies conventional lunar norms. Unlike most moons in our solar system, Triton orbits Neptune in a retrograde direction, meaning it moves in the opposite direction to its planet's rotation. This peculiar motion suggests that Triton did not form an orbit around Neptune, but was instead captured by the planet's gravity. The leading theory proposes that Triton originated in the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. Its capture by Neptune's gravity would have been a chaotic event, likely causing significant tidal interactions that continue to influence Triton's geology and internal processes today. One of the most striking features of Triton is its cantaloupe terrain, a unique surface texture that resembles the skin of a cantaloupe melon. This terrain is characterized by a series of irregular, overlapping ridges and depressions, creating a hummocky landscape. The cantaloupe terrain is thought to be the result of extensive resurfacing events, possibly driven by cryovolcanic activity or diapirism, where buoyant, warm ice rises through the colder, denser surface layers. The interaction between Triton's internal heat and its icy shell has led to a complex and dynamic surface geology, making it a fascinating subject for planetary scientists. Tidal heating plays a crucial role in Triton's geology and internal dynamics. As Triton orbits Neptune in a retrograde motion, the gravitational forces between the Moon and the planet induce tidal flexing. This process generates frictional heat within Triton's interior, providing the energy necessary for geological activity. The heat is sufficient to maintain a subsurface ocean of liquid water, which could potentially harbor life. The tidal forces also contribute to the Moon's geological features, such as the cantaloupe terrain and the vast polar ice caps. Understanding Triton's tidal heating mechanisms offers valuable insights into the processes that shape icy moons and their potential habitability. The retrograde orbit of Triton has significant implications for its long-term stability. Over time, tidal interactions between Triton and Neptune are causing the Moon's orbit to decay, gradually bringing it closer to the planet. Eventually, Triton may cross the Roche limit, the distance within which tidal forces would tear the Moon apart, forming a ring system around Neptune. This process is a slow one, taking billions of years, but it highlights the dynamic and ever-changing nature of celestial bodies. Triton's unique characteristics and its eventual fate make it a compelling subject for study, offering a window into the complex interactions that shape our solar system. Neptune's gravitational influence. Triton, Neptune's largest moon, is a captivating celestial body that orbits its planet in a retrograde motion. This means it moves in the opposite direction to Neptune's rotation, a behavior that sets it apart from most other moons in our solar system. The retrograde orbit is a strong indicator that Triton did not form an orbit around Neptune, but was instead captured by the planet's gravity. This capture likely occurred billions of years ago, when Triton was a wandering object in the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. Neptune's gravitational influence was so powerful that it managed to snag Triton from its original path, pulling it into a bound orbit. The gravitational dance between Neptune and Triton is a complex one. Over time, Neptune's gravity has had a profound effect on Triton's orbit, causing it to become more circular and closer to the planet. This process, known as tidal evolution, has also resulted in Triton's orbit becoming synchronous, meaning it now takes the same amount of time to rotate on its axis as it does to orbit Neptune. This is why Triton always shows the same face to Neptune, much like our own moon does to Earth. The gravitational interaction has also caused Triton to heat up, leading to geological activity that has shaped its unique surface. Speaking of Triton's surface, it is one of the most intriguing in our solar system. The Moon is covered in a vast, icy plain that is crisscrossed by ridges and valleys, giving it a distinctive cantaloupe-like appearance. These features are thought to be the result of upwelling diapirs, which are large blobs of less dense material that rise through the denser material beneath the surface. This geological activity is likely driven by the heat generated from Neptune's gravitational influence. The cantaloupe terrain is not the only interesting feature on Triton. The Moon also has geysers that spew nitrogen gas and dust particles several kilometers into the sky, creating dark streaks on its surface. Triton's captured origin and retrograde orbit provide valuable insights into the dynamic processes that shape our solar system. The Moon's unique features and ongoing geological activity serve as a testament to the powerful influence of Neptune's gravity. As we continue to study Triton, we gain a better understanding of the complex interactions that occur between planets and their moons, as well as the fascinating history of our solar system's formation and evolution. The fate of Triton. Triton, Neptune's largest moon, is a captivating celestial body that orbits its planet in a retrograde motion. This means it moves in the opposite direction to Neptune's rotation, a behavior that sets it apart from most of the solar system's moons. Such an orbit is a strong indicator that Triton did not form an orbit around Neptune, but was instead captured by the planet's gravity. This capture likely occurred billions of years ago, a violent event that would have disrupted Triton's original path and settled it into its current, unusual orbit. The moon's retrograde motion is not just a quirk. It provides crucial clues about its origins and the dynamic history of the Neptune system. Triton's surface is a stark contrast to the icy moons typically found around gas giants. It boasts a unique terrain known as the cantaloupe terrain, characterized by its bumpy, irregular surface that resembles the skin of a cantaloupe melon. This terrain is thought to be the result of extensive resurfacing events, possibly driven by cryovolcanic activity, where icy materials from the moon's interior were expelled onto the surface. The cantaloupe texture is a testament to Triton's geological activity, hinting at a complex internal structure and a history of dramatic changes. These features are not just visually striking. They offer insights into the moon's composition and the processes that have shaped it over time. The moon's captured nature suggests it originated in the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. This origin story is supported by Triton's composition, which is rich in nitrogen and methane ices, similar to many Kuiper Belt objects. The capture of such a large body would have had profound effects on the Neptune system, potentially disrupting other moons and rings. Triton's retrograde orbit and cantaloupe terrain are just the surface manifestations of a much deeper, more tumultuous past. Understanding Triton's fate, its capture, its geological evolution, and its current state provides a window into the broader dynamics of the outer solar system. It's a story of cosmic collisions, gravitational tugs, and the relentless forces that shape the worlds around us. A doomed moon. Triton, Neptune's largest moon, is a captivating celestial body that orbits its planet in a peculiar manner. Unlike most moons in our solar system, Triton moves in a retrograde orbit, meaning it circles Neptune in the opposite direction to the planet's rotation. This backward motion is a strong indicator that Triton did not form an orbit around Neptune, but was instead captured by the planet's gravity. The moon's unusual trajectory suggests a violent past, likely involving a close encounter with Neptune that slowed Triton down enough for the planet's gravity to seize it. This capture event probably disrupted Triton's original orbit, leaving it in the retrograde path observed today. The moon's eccentric orbit and inclination further support this theory, as they are characteristic of captured objects rather than those that formed in situ. Triton's surface is a stark contrast to the icy moons typically found around gas giants. Instead of a smooth, cratered expanse, Triton boasts a unique and rugged terrain known as the cantaloupe terrain. This name comes from the moon's resemblance to the skin of a cantaloupe melon, with a complex network of ridges and grooves crisscrossing its surface. These features are thought to be the result of extensive tectonic activity, driven by the heat generated from Triton's capture and subsequent orbital evolution. The cantaloupe terrain is a testament to the moon's dynamic past, with ridges that can reach hundreds of meters in height and stretch for tens of kilometers. This terrain is not uniform, but varies across the moon's surface, with some regions appearing more heavily grooved than others. The cantaloupe terrain is not Triton's only distinctive feature. The moon also hosts a variety of other geological wonders, including vast polar ice caps composed of nitrogen and methane. These ice caps undergo seasonal changes, growing and shrinking as Triton's distance from the sun varies. Additionally, Triton is one of the few moons in the solar system known to be geologically active, with evidence of cryovolcanism, volcanic activity that involves the eruption of ice and other volatile compounds instead of molten rock. This activity is thought to be driven by the heat generated from the tidal forces exerted by Neptune, which flexes and heats Triton's interior. The moon's surface also bears the scars of impact craters, albeit fewer than expected, suggesting that geological processes have resurfaced much of Triton's surface over time. Triton's origins are shrouded in mystery, but its retrograde orbit and unique surface features hint at a captivating history. The moon's capture by Neptune likely occurred billions of years ago, when the solar system was a more chaotic place. Triton's original home was probably the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. This region is teeming with small, primitive objects that have remained relatively unchanged since the solar system's formation. Triton's capture would have been a violent event, with the moon's original orbit disrupted and its surface reshaped by the gravitational forces at play. The moon's subsequent evolution, driven by tidal heating and geological activity, has resulted in the complex and captivating world we see today. Triton's story is a reminder of the dynamic and ever-changing nature of our solar system, where even the most seemingly stable objects can have tumultuous pasts. The Neptune-Triton system. In the far reaches of our solar system, Neptune's largest moon, Triton, dances in an unusual ballet. Unlike most moons, Triton orbits Neptune in a retrograde motion, moving in the opposite direction to the planet's rotation. This backward orbit is a strong indicator that Triton didn't form in place, but was instead captured by Neptune's gravity. The moon's elliptical path and inclined orbit further support this theory. Scientists believe Triton was once a solitary traveler in the Kuiper Belt, a vast region of icy bodies beyond Neptune's orbit. Its capture by Neptune's gravity is a dramatic tale of celestial mechanics, a dance that likely involved tidal forces and orbital resonances. Triton's surface is a stark contrast to the icy moons of Saturn or Jupiter. It's a world of dramatic topography, dominated by what scientists call the cantaloupe terrain. This unique landscape is characterized by a series of irregular, cantaloupe-like ridges and depressions. These features are thought to be the result of icy volcanism, where nitrogen and water ice have erupted onto the surface. The cantaloupe terrain covers a significant portion of Triton's surface, hinting at a complex geological history. The moon's surface is also marked by few impact craters, suggesting it's relatively young in geological terms. This is a world that's been actively reshaped, perhaps by the same forces that caused its capture. The retrograde orbit and cantaloupe terrain are just the beginning of Triton's mysteries. The moon's surface is also dotted with geysers that spew nitrogen gas and dark particles into the thin atmosphere. These geysers are another sign of Triton's active geology. The moon's thin atmosphere is composed mainly of nitrogen, with traces of methane and carbon monoxide. It's a dynamic system, driven by seasonal changes and perhaps by the heat generated from Triton's capture. The moon's interior is likely differentiated, with a rocky core surrounded by a mantle of water ice. This internal structure is another clue to Triton's captured origins, as it suggests a history of heating and differentiation. Triton's retrograde orbit and unique surface features make it a fascinating subject for study. The moon's captured origins offer insights into the dynamics of the outer solar system. Its active geology provides a window into the processes that shape icy worlds, and its thin atmosphere is a case study in the interactions between a moon and its parent planet. Triton is more than just a curiosity. It's a key to understanding the complex history of our solar system. Future exploration. Triton, Neptune's largest moon, is a captivating celestial body that orbits its planet in a retrograde motion, meaning it moves in the opposite direction to Neptune's rotation. This peculiar behavior hints at Triton's violent past, likely captured by Neptune's gravity from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. Future exploration of Triton could unravel mysteries about the early solar system and the processes that shaped it. Scientists are particularly interested in studying Triton's unique geology, including its distinctive cantaloupe-like terrain, which is characterized by irregular, cratered, and ridged surfaces resembling the skin of a cantaloupe melon. This terrain is thought to have formed from a combination of icy volcanism and tectonic activity, driven by the internal heat generated by Triton's capture and subsequent orbital evolution. The retrograde orbit of Triton provides a rare opportunity to study the dynamics of captured objects in our solar system. Future missions could focus on understanding the moon's orbital evolution and the tidal forces that have shaped its interior. These forces likely contributed to the partial melting of Triton's interior, leading to the formation of a subsurface ocean and the geologic activity observed on its surface. Exploring Triton could also shed light on the composition and evolution of Kuiper Belt objects, offering insights into the building blocks of the solar system. The moon's surface is rich in nitrogen, methane, and carbon monoxide ices, which are also found in comets and other Kuiper Belt objects. Studying these ices could provide clues about the chemical processes that occurred in the early solar system. One of the most intriguing aspects of Triton's cantaloupe terrain is the presence of cryovolcanic features, where icy materials are ejected from the interior onto the surface. These features include smooth plains, ridges, and pits, which are thought to be the result of icy lava flows and explosive eruptions. Future exploration could involve detailed mapping and analysis of these features to understand the processes driving Triton's geologic activity. Additionally, Triton's thin atmosphere, composed mainly of nitrogen with traces of methane and carbon monoxide, could provide valuable information about the Moon's interaction with solar radiation and its potential for supporting complex chemistry. Studying this atmosphere could also help scientists understand the processes that lead to the formation of atmospheres on other icy bodies in the outer solar system. Future missions to Triton could leverage advanced technologies such as high-resolution imaging, spectroscopy, and in situ measurements to gather detailed data about the Moon's surface and interior. For instance, a lander mission could directly analyze the composition of Triton's ices and study the geologic processes shaping its surface. Furthermore, studying Triton's gravitational field and magnetic environment could provide insights into its internal structure and the presence of a subsurface ocean. Such a mission would not only enhance our understanding of Triton, but also contribute to our knowledge of the broader solar system and the processes that govern the evolution of planetary bodies. The exploration of Triton holds immense potential for uncovering the secrets of our solar system's past and the dynamics of captured objects in the outer reaches of our cosmic neighborhood. Unraveling the mystery. Triton, Neptune's largest moon, is a celestial body that has long captivated astronomers and space enthusiasts alike. Its most intriguing feature is its retrograde orbit, a characteristic that sets it apart from most other moons in our solar system. Unlike the majority of moons, which orbit their planets in the same direction as their planet's rotation, Triton orbits Neptune in the opposite direction. This peculiar motion suggests a violent past, hinting that Triton may not have originated as a satellite of Neptune, but rather was captured by the planet's gravity. The Moon's retrograde orbit is a strong indicator of its exotic origins, possibly as a Kuiper Belt object, a region of the solar system beyond Neptune's orbit filled with icy bodies. The surface of Triton is equally fascinating, marked by a unique terrain known as the cantaloupe terrain. This distinctive landscape is characterized by a series of irregular, cantaloupe-like bumps and depressions that cover much of the Moon's surface. The cantaloupe terrain is thought to be the result of extensive volcanic activity, driven by the internal heat generated by Triton's captured orbit. As Triton was pulled into Neptune's gravitational influence, tidal forces likely caused the Moon to heat up, leading to the eruption of icy volcanoes and the formation of its unusual surface features. The cantaloupe terrain is a testament to the dynamic and tumultuous history of this enigmatic moon. Triton's captured Kuiper Belt object origins are further supported by its composition and other surface features. The Moon is composed primarily of nitrogen, methane, and water ice, similar to the composition of many Kuiper Belt objects. Additionally, Triton's surface exhibits a variety of geological features, including cryovolcanic plumes, geysers, and a thin atmosphere, all of which are consistent with the characteristics of captured objects from the outer solar system. The study of Triton provides valuable insights into the processes that shape the outer reaches of our solar system and the complex interactions between planets and their moons. Its retrograde orbit, cantaloupe terrain, and captured origins make Triton a fascinating subject of study, offering a glimpse into the dynamic and ever-changing nature of our cosmic neighborhood. As we wrap up our exploration of Triton, Neptune's enigmatic moon, let's recap the key points that make it such a captivating world. Triton's retrograde orbit, spinning in the opposite direction to Neptune's rotation, is a strong indicator that this moon didn't form in place, but was likely captured from the distant Kuiper Belt. This violent past is etched into its surface, most notably in the form of its striking cantaloupe terrain, a bizarre landscape of intersecting ridges and valleys that resembles the skin of the melon. This terrain is thought to be the result of icy volcanic activity, a testament to Triton's dynamic and complex history. What makes Triton truly fascinating is its defiance of the norm. It's a moon that marches to the beat of its own drum, a captured object that found a new home and adapted in ways that continue to puzzle and intrigue scientists. As we gaze at its icy surface and ponder its origins, we can't help but feel a sense of wonder at the cosmic dance that brought this moon to where it is today. If Triton's mysteries have sparked your curiosity, stay tuned for our next exploration. We'll be diving into the enigmatic world of Pluto, another former planet and Kuiper Belt object that holds secrets of its own. Until then, keep looking up at the night sky and let your imagination soar with the mysteries of our solar system. Who knows what other captivating stories are waiting to be discovered?